There are several modules and packages imported into this code from different libraries, including pandas, numpy, and sklearn. A division line imported from future ensures that floating point numbers are used throughout the calculation, allowing for more precise calculations. Various functions from these libraries are then imported into the rest of the code, including data processing and machine learning algorithms, as well as neural network tools. This simplifies the process of loading and utilizing these tools and functions. This file is imported into Python environment using pandas library. 5 companies are represented in the CT file: Reliance, TIFF, that's it, and Infosys. The dataset covers a period of 10 years and includes a total of 10 years worth of stock data. In the following screen, the data frame shows the first few rows of the data. The stock data for the specified companies over the past 10 years can be easily accessed and analyzed. A data frame called diff is converted into a datetime column, datetime 64, and using this code. Date column values will now be in a data and time format that can be easily manipulated and analyzed. This change is displayed by tail, which shows the last 5 rows of the data frame. Stock data is being updated with new columns in this code. A new column called signal is created and its values are all set to 0. After that, it calculates 2 moving averages, a shorter one with 30 windows, and a longer one with 120 windows. Moving averages based on close are displayed here. Lastly, it compares the 2 moving averages, and if the shorter one is larger than the longer one, the signal column is set to 1, 0, otherwise it is set to 0. Through the use of technical indicators, one can identify trends in stock data. In this code, an exponential moving average function called AMA is created. Using a moving average calculation, recent data points are given more weight than older data points. It takes in a data frame diff and a value and as parameters. Using the closed column from the data frame, it calculates the exponential moving average using the un function from the pandas library. A new series AMA is created with the calculated value and name as the result. In the end, the function returns the AMA series. In order to calculate 3 different exponential moving averages, the code calls the AMA function 3 times, within 21, 63, and 252 set to different values. As a result, 3 new columns AMA21, AMA63, and AMA152 are created in the original data frame. A tail function is used to display the last few rows of the updated data frame. It enables the calculation and visualization of multiple exponential moving averages from the same dataset easily. ROC is a function defined here that takes 2 parameters diff and n. Diff represents a data frame and n represents a number. Using the function, you can determine the percentage change in a variable over time. During the first line of the function, the value of the variable m will be calculated by subtracting the current value from the value in periods ago. It divides m and calculates the rate of change by shifting the data frame and periods back and assigning it to a new variable named n. In the third line of the function, ROC is created by multiplying m by n and then dividing the result by 100 to determine the rate of change. An ROC series with this value is then assigned a name indicating the calculation period. A series of ROC values is returned by the final line of the function. 2 lines of code use the ROC function to calculate the rate of change for the closed variable in the data frame over 21 and 63 period lengths. The results are then assigned to 2 new columns in the table called RO21 and RO63s. This code calculates a variable's rate of change over a specified period of time and adds it to a data frame to be analyzed. Using this code, you can calculate the price momentum for a given data frame diff over a given period and using a function called mom that takes 2 parameters diff and n. By comparing the data frame to the data from n periods ago, the function creates a new series called momentum. In the following series, it returns the result. After calculating the price momentum over 21 and 63 periods for the closed column of the data frame, the code adds these new series as mom21 and mom63 to the original data frame. The relative strength index RSEQ for a particular stock or financial asset can be calculated using this code. It is parameterized by a series of price data and a period of time. It assigns the difference between consecutive values in the series to a variable called delta. Then it creates 2 new series, one for positive changes U and one for negative changes D. For the positive changes, values above 0 in the delta series are copied over. Whereas for the negative changes, values below 0 are multiplied by 1. New series are created by averaging the first period of values in the original delta series. Each series is then truncated with the first value of period 1. RS is calculated by dividing the rolling mean of positive changes by the rolling mean of negative changes. In the end, the RC is calculated by subtracting 100 from 100 divided by 1 plus the relative strength. A data frame is then constructed for 3 time periods 21, 63s, and 252. Using a mathematical formula, the code calculates the RSIC for a set of price data over a specified period of time. Traders and investors can use this data to determine whether a stock or asset is strong or weak and make investment decisions accordingly. The stochastic oscillator is a common financial market technical indicator calculated using this code. It compares a security's current closing price with its price range over a certain time period, typically 14 days. Trading decisions are often based on this indicator, which is used to identify potential reversal points. In the code, the fast stochastic oscillator is first calculated by the function stock. Inputs include the closing price of a security, its lowest price, and its highest price, as well as the time period n. The stochastic oscillator based on this input is returned as a second function. STOB calculates the slow stochastic oscillator, which is the 3-period moving average of the fast stochastic oscillator. Also called stock, this function returns the slow stochastic oscillator's value with the same parameters. In the next section of code, we calculate the stochastic oscillator for different time periods, such as 21 days, 63 days, and 252 days, and add these values to the data frame diff. By comparing the stochastic oscillator over different time periods, one can see how it changes over time. It calculates fast and slow stochastic oscillators, then adds them to a data frame for further analysis in financial markets. It creates a function called MA that calculates a moving average with a specific period based on a given dataset. This function takes 2 arguments def and n, which represent the dataset and the period, respectively. This line creates a series called MA and assigns it the value of the average of the close column. The rolling function specifies the number of periods to be used, with the minimum number of periods set to n. This creates the moving average for the specified period. A series containing the parameter period and the name MA is returned next. 3 next lines of code call the MA function with different period values 21, 63, and 252, and assign the resulting series to columns MA21s, MA63, and MA252. It allows users to easily calculate and view moving averages based on different time periods. As a final step, the code returns the final few rows of the data set with moving averages calculated for each column. Any row in a data frame that contains a non-number NaN value is handled by this code. To determine how many rows contain a NaN value in the data frames, the first line checks the columns. Defubdef dropNet creates a new data frame called defub with all rows left except for those containing a NaN. Thirdly, defub hisnull sum is used to ensure that no rows contain a NaN value in the new data frame. Lastly, defub head prints out the first few rows of the new data frame so that we can see the results of removing the NaN rows. The purpose of this code is to remove any rows with missing or unusable data from a data frame. Data frame defub is taken and the column labeled signal is removed. A variable called x1 has been assigned to the remaining data frame. Following that, the training and testing data are stored in 2 additional variables, xtrain and xtest. A model is developed using training data, while its performance is evaluated with testing data. By defining a test size and a random state parameter, the code can make sure the data split will be consistent every time. The code prints out the number of rows and columns in each dataset as well as its shape or dimensions. Robust Sailor is imported from the Sclern library with an import statement. In order to create xtrain1, certain columns from the xtrain dataset are dropped. Dropping are the columns close, date, symbol, high, low, open, volume, short mab, and long mab. As a result, we are left with only columns containing numerical data. Xtest dataset is then similarly transformed, with the same columns dropped from the new variable xtest1. As a next step, you should create an instance of the robust Sailor function called RS. As well as the xtrain dataset, the xtest dataset will be transformed with the Sailor. Sellers are fitted to the X-Train-1 data, which essentially finds mean and standard deviation. A transformed dataset called X-Train-STD and a dataset called X-Test-STD is created using the fitted seller. Certain machine learning algorithms will be easier to use with these standardized datasets, since they have a mean of 0 and a standard deviation of 1. With this code, you will be able to create a list named dataSelected that consists of 4 different machine learning models: ken or k nearest neighbors, card or classification and regression trees, fitting or support vector machine, and RF or random forest. Next, the system creates a list that stores the estimated results of each model, called results, and a list that contains names for the models, called names. The next step is to define the metrics that will be used for evaluating the system, including the phone score, accuracy, precision, and recall. As a next step, it computes the specified metrics using each model and data selected, looping through each and calculating cross-validation on the training data using that model. A results and names list is created from the results. At the end of the code, the output for each model is printed, along with the name of the model, the mean of the cross-validation results, and the standard deviation. The model with the most accurate and consistent performance can be compared. It creates an algorithm comparison figure from Matplotlib. A new subplot is added to the figure, with 111 as its specific position, to plot results of a dataset called results. It uses the boxplot function. In addition, the x-axis tick marks are labeled with the names of the data, and the plot is displayed. Basically, this code compares results for different algorithms in a dataset visually. First, this code creates a new data frame called defubs by dropping certain columns from an existing data frame named defub. Symbol ID close, high, low, open, volume, short map, and long map or among the columns dropped. In turn, this new data frame is displayed with the head method. Following this, we create a new variable x by removing the signal column from the defubs data frame, and a new variable y by including only the signal column in it. An algorithm is being prepared for use in a machine learning model. We then create a random forest classifier model with 500 estimators. After fitting the random forest classifier function to the x and y variables, by using the random state-tone argument, a reproducible result is guaranteed, and the inJobs1 parameter enables the model to run parallel on all available processors. The model can thus be trained efficiently as a result. In this code, a data frame named importance is created that contains a single column of values representing the importance of each feature in a machine learning model, most likely a random forest. Values are calculated by multiplying feature importance scores by 100 for each feature. The column names of the new data frame were used as indexes to find the features in a data frame called X. Assigning high priority to features with lower importance, the importance data frame is printed in ascending order. In order to create a bar graph, the code plots the values from the importance data frame horizontally. A red bar is used to distinguish the bars, and a variable importance axis label will appear at the top. In Ga legend, the legend of the graph is removed. In general, this code allows us to visualize each feature's importance in a machine learning model, with lower importance features listed first and the values represented in a red bar graph. Understanding which features have the greatest impact on the performance of a model is possible with this information. The sliding window function is used to create the LSM model. Dataset data and window size are parameters. It is set to 1 by default. For this reason, a copy of the dataset is made data S in order to avoid manipulating the original. Next, a for loop is used to iterate through the data's columns, equal to the window size. During each iteration, the function adds a new column to the dataset, which has values shifted by ion rows. A moving window of data is created by this method. At the end, any missing values are removed, and the updated dataset with the sliding window is returned. Using this function, you pass DSM, which represents the data frame containing the data to be modeled, and window, which represents the window size. The first line of the function creates a scalar object that will be used for transforming the data into a range between 0 and 1, which is useful for certain machine learning algorithms. Following the creation of the original data frame DSM, we create a new data frame DT that contains the scaled data for those features. Using the random forest algorithm, these features are selected according to their calculated importance values. As a result of the transformation, X contains the selected features from DZ. and using the create window function, a window of sequences is created. A reshaped version of X is returned by the create window function with each sequence containing window 1 features. To prepare data for use in time series forecasting models, this step is necessary. In the final step, X is transformed into a format that can be used by machine learning algorithms, with the first dimension representing the number of sequences, the second dimension representing the size of the window, and the third dimension representing the number of features. Also, Y is created, containing the sequence targets. Using the code described above, we take in a data frame. Select the 5 most important features, scale them, create sequences based on a specified window size, and prepare the features for machine learning. In this code, time series data is predicted using long short-term memory and convolutional one-dimensional convolutional layers. There are 2 inputs to the model. Window is the size of the input sequence and features is the number of features. In the first step, the model is initialized in the form of a sequential model. There are sequentially added layers. A convolutional layer is then added with a specified input shape, number of filters, kernel size, stride, activation function, and padding parameters. Data is processed by the convolutional layer to extract features. Sum is next, followed by another convolutional layer with similar parameters that returns sequences rather than just final results. A dataset with temporal dependencies can benefit from this approach. This is followed by an addition of a dropout layer with a dropout rate of 0.5 to prevent the model from overfitting. Next, an LSM layer of 200 units is added, which only outputs the final prediction due to a return sequence of false. In addition to the dropout layer, 2 dense layers are added, each of differing size and activation function, in the final prediction. These layers are responsible. A mean squared error loss function and atom optimizer are then used to compile the model. In the end, the compiled model is returned. An import statement imports a function named data to model from a file called defubs and initializes a variable called window with 5 as its value. Next, 2 variables x and y are assigned values using the function. To prepare data for modeling, this function is responsible. Following that, the code creates a variable named test and sets its value to 100. After splitting the data into training and testing sets, the code runs. Test data is assigned to variables xTest and yTest, while training data is assigned to variables xTrain and yTrain. Training data consists of all x and y data, except for the last 100. Approximately 100 data points comprise the testing data. In general, this code splits the data into training and testing sets for modeling. The code below creates a model known as model LSM that uses LSTMs, which are a type of neural network. Specifically, a model LSM neural network has been used here to learn patterns by taking a sequence of data points one at a time. For creating the model, we need to specify the input window size, defined as window-1, with 5 output neurons. It is possible to view a summary of the model, including its layers, output shape, and number of parameters by calling model LSM. Summary, model structure, and complexity can be understood using this information. Using this code, we create a learning rate reduction object that monitors validation loss, waits 25 epochs before adjusting the learning rate, and prints a message when a reduction is made to the learning rate. When the factor is set to 0.25, the learning rate will be decreased every time by 25 apparent, and the lowest learning rate is set to 0.1 during training. This enables machine learning models to improve overall accuracy by adjusting the learning rate. It delays reducing the learning rate for a longer time while reducing the factor value for a smaller adjustment. The learning rate won't drop too fast, preventing the model from getting stuck in a local minimum. A machine learning model could potentially be improved by using this code to optimize the learning rate during training. By fitting training data to LSM models, this code trains them. Models are trained for 20 epochs, which means they go through datasets 20 times. We train the model with 24 data points per batch. Additionally, the validation dataset helps to evaluate the model's performance on data that hasn't been trained yet. During training, there is also a function called learning rate reduction, which can reduce the learning rate. Data points are not shuffled as specified in the code, so the order of the data points is not altered. Once the model is fully trained, it can make predictions about new data. In this code, a line plot is created that visualizes the training and testing losses over different epochs. Training and testing losses are plotted by pult, plot, pult, title, pult, label, and pult. Label add titles, label y-axis as loss, and label x-axis as epoch, respectively. A legend is added to the plot by using the pult legend function. Pult shows the plot on the screen at the end. It is responsible for saving the pre-trained LSM model into the file LSM weights. 5. During the training process, the model will have learned and optimized all information and parameters. This allows us to reload the model at a later date without retraining it from scratch, which can save us time and resources. As the weights are saved, we can use them later to make predictions or continue training the model. Overall, this code ensures that the trained model is preserved and accessible in the future. In this line, model LSM is used to predict X test data using the trained model. Model LSM. In ypred LSM, these predictions are then stored. It then calculates the difference in predicted values for each consecutive pair in ypred LSM. Diff uses the array of predictions and subtracts each element from the one prior. WLSM stores the resulting array. Lastly, the code uses the NIP maximum function to find the maximum of each element in the array WLSM. A negative value will be removed from the array and set to 0 as a result. It is stored in VLSM as the resulting array, using the training model. This code makes predictions about the test data, then subtracts any negative values from each pair of predictions. The code creates a function for calculating buy-sell indicators based on a stock price list and a set of values from an LSM model. By iterating through the list of LSM values, the function will determine when to buy or sell the stock. It creates 3 empty lists: buy, sell, and flag. Eventually, the for loop iterates through the VLSM list and checks each value. The LSM model predicts a buy signal when index I equals 1. When the flag variable is 0, the code indicates we have not yet purchased the stock and a buy signal has been received. So the current price at index I is added to the buy list and an AN is added to the sell list, indicating no sale has taken place. It means that the model has not predicted a buy signal if the LSM value is not equal to 1. Next, the code checks if the flag variable equals 1, but if it doesn't, it passes. Since we currently have stock in our possession, an AN is appended to the buy list to indicate that further purchases are not needed, and the current price at index I is appended to the sell list to indicate that now is the best time to sell. It means neither a buy nor sell signal has been detected, so NANs are added to both the buy and sell lists to indicate that no action should be taken. By the end of the for loop, the buy and sell lists are returned as the final outputs of the function. It performs stock prediction using an LSM model, returning 2 lists indicating when to buy and sell a stock, as well as timestamps for those transactions. A figure with the size of third extent is created and plots the AGI close prices of a stock, colored blue and labeled as price, based on a specific algorithm. It determines when to purchase and sell the stock using a function called buy sell indicator. In addition, the code creates scatter plots, colored green for buy moments and red for sell moments, respectively. On the y-axis is the price, while the co-axis is the number of days. In addition to a legend and title, the figure includes a caption. The final step is to display the figure. Infosys is the only stock involved in this process.